Hello and welcome. This is the recitation video for our lecture video concerning basics of fluid mechanics. So without further ado, let's start. So here we are with problem 1. We have a velocity field given to us in the vector form. We have 4x squared y in I direction and then xy squared in j direction. This is defining the velocity field. We are asked to find the equation for streamlines. And also, we are asked to plot several other streamlines. So let's start with the definition of a streamline. We know that the streamline is a line that is always tangent to the direction of the velocity. Based on this definition, we have this equation. In a 2D plane, xy plane, just like the problem that we have, we can write dy over dx is equal to y component of the velocity, small letter v, over the x component of the velocity, small letter u. Now let's play with this equation. Now the y component of the velocity, by looking at the velocity field equation, is xy squared. We can also find the x component of the velocity u by looking at the same equation. It's 4x squared y. I can simplify this equation a bit. Doing some simple algebra, I get y over 4x. I can continue playing with this equation. I can say, okay, dy over y is dx over 4x. Now I'm ready to make the integral. Integral dy over y is equal to the integral of dx over 4x. The left-hand side of this integral is natural log of y. The right-hand side of this equation, this integral, is 1/4 natural log of x plus an integral constant c. Now this is a log equation, natural log equation, and as a result, I can play with the constant, with the integral constant c a little. I can say that natural log of y is actually natural log of c x to the power of 1/4. Now what I did is I know that the coefficient of the natural log can be plugged in inside the natural log as a power term. So that's why we have x to the power of 1/4. And then I can rewrite the constant c because it's just a constant. I can say, okay, instead of constant c, I can say natural log of the constant c. It's okay, I can do that. Now the natural log of x to the power of 1/4 plus the natural log of c is equal to natural log of c times x to the power of 1/4. Okay, so this equation, we can still simplify this equation a little bit. I can say, now that the both sides are in natural log formation, I can say, okay, y is actually equal to cx to the power of 1/4. So this is the equation that governs the streamlines in this flow field. C is a constant here, and depending on the value of the C, you will get different streamlines. Now, from now on, in order to plot these lines, you have two different options. You can change C arbitrarily, and you will get streamlines that match the C that you chose, or you can focus on certain points inside the flow field and focus on finding the streamline that passes through those lines. For example, if you really want to know the equation for the streamline that passes through the point 1 and 1, you can find the C for this specific streamline first and then plot that. So we are looking for a streamline that passes through 1 and 1. We need to find C. So what I can do is say, okay, y is 1, c is unknown, x is 1 to the power of 1/4. Basically, this is a very simple equation that gives you c is equal to 1. So this equation here, y equals x to the power of 1/4, is the equation for the streamline that passes through point 1 and 1. Okay, now to the next part of this question, plotting the actual streamlines. So I'm using this plot generator on this website, and you can see the address here. I'm going to put the link to this website in the description of the video as well. Now let's try and plot some of those streamlines. So we found that the equation for the streamline is y is equal to a constant c times x to the power of 1/4. Now this website gives you the option to change the value of c and see how it affects your plot. So for c equal to 1, this is the streamline. You can change c and you can see that the streamline starts to change on the graph, right? So this is pretty handy if you want to know how the streamlines behave based on the constant c. However, maybe you want to see a few different streamlines at the same time. You can always do that. I'm going to show you the streamline that passes through point 1 and 1, the blue line here. I'm going to show you another streamline. Maybe C is 2 this time. This is the streamline for C equal to 2, the green line. You can continue to play with this and find different streamlines. You can obviously have C as a negative value and so on. So these are the green, the light blue, and the dark blue are different streamlines for different values of C. And the black line here is the general equation where you can change the value with C using this slide bar. So these are a few examples of streamlines in this flow field. Okay, let's move on to problem 2. Again, we are given a velocity field in the form of a vector, and we are asked to find the equation for streamlines. This time, however, it is a bit different in a sense that this equation is not only dependent on x and y, but also on time. So we are dealing with a transient or an unsteady velocity field. Now the general equation that we follow is the same as problem 1. We can say dy over dx is equal to small letter v over small letter u, velocity components in y and x direction respectively. So let's make that fraction here. Small letter v in this case is negative x, and small letter u is 4yt. Let's play with this equation just like the last time. I can say, okay, y dy is equal to negative x over 4t dx. Now, something that you need to pay attention to is that time here is an independent variable. X and y here in this equation are related through this equation that we had. And as you can see, it is an ODE. It's an equation based on the differentials of both y and x. And so we had to do a separation of variables for x and y to get an equation that is integrable. However, time is independent of either x and y here, so it can be treated as a constant when making the integrals based on x and y. All right, so with that out of the way, let's make the integral. I have integral of y dy is equal to integral of negative x over 4t dx. Left-hand side of this equation gives me y squared over 2. The right-hand side of this equation gives me negative x squared over 8t plus c, the integral constant here. Playing with this equation a little more gives me y squared plus x squared over for t is equal to c. Now this is the streamline equation that governs this flow field. There is something very interesting about this equation. This is an ellipse equation. So the streamlines in this flow field look like ellipses, concentric ellipses. Now the second part of the question asks us to plot several streamlines at different times, namely t equal to 0, 2, and 10 seconds. Looking at this equation, you can see that for t equal to 2 and 10 seconds, there is no problem here. T, as I said, is just like a constant for this equation. So you could just plug a 2 or 10 in for t, and you can start plotting different streamlines. However, for t equal to 0, we have a problem. Time is in the denominator of the x term here, and if you put 0 there, you have a 0 in the denominator, which is never a good thing. For the special case of t equal to 0, we have to revisit the original equation. So for t equal to 0 only, I'm going to revisit the velocity field equation. I will get velocity is 4y t in the I direction, negative x j direction. Now, if t is equal to 0, this term drops, and I end up with the velocity field is negative x in j direction. So what does this mean? It means that initially, when time is 0, the velocity field is parallel, at every point is parallel to the y-axis. As you can see, there is no I term or any velocity component in the direction of x-axis. So at every point, the flow is parallel to the y-axis. So if I want to plot the streamlines for this situation, I will end up with something like this. If this is my x-axis and this is my y-axis, then the streamlines at t equal to 0 look like this. They are all parallel to the y-axis. The direction of the streamline that kind of represents the direction of the flow, remember streamlines are always tangent to the flow, the velocity field, is defined by this equation. Velocity is negative x in j direction. So on the right-hand side of the x-axis, where the values for x are positive, the streamlines are in the negative y direction. On the left-hand side of the x-axis, where the values of x are negative, the direction of the streamlines will be in the positive y direction. So here we are with this website again. I'm just going to try and draw some streamlines for the second problem. We already did draw the streamlines for t equal to 0 seconds. Now I'm going to try and draw the streamlines for t equal to 2 seconds and 10 seconds. So let's start with 2 seconds. I get y squared plus x squared over, now we are talking about t equal to 2, so 4 times 2 is 8, is equal to c. Now here I can play with the value of the c and generate different streamlines. Okay, so at time t equal to 2 seconds, these are different streamlines. Again, you may want to have them at the same time on your screen. So I'm going to rewrite this equation a few times. So the black, red, and blue ellipses here are for these 3 different values of c. The green line is the ellipse that you can generate by changing the c manually on this slide bar. Now this was for t equal to 2 seconds. Let's do the same thing for t equal to 10 seconds. So the equation turns to y squared plus x squared over, now 4 times 10 is 40, is equal to, again, different values of c. Now, this time, you can see that the ellipses are a bit more elongated along the x-axis. Now, why is that? Let's take a look at the general equation. So the general equation for streamlines is y squared plus x squared over 4 times t is equal to c, right? Again, you have the option to treat c and t as constants with sliders here, so let's do it. Now, for a constant value of c, when you increase t, what is actually happening? So, if you take a look at the equation here, t is in the denominator, right? Now, when increasing t, you're actually increasing the denominator of the x term. Now, generally speaking, when t reaches very high values, let's say theoretically it reaches infinity, the denominator of the x term gets so big that we can assume that x squared over 4t goes to 0. In that case, the streamline equation basically becomes y is equal to a constant number. For example, if you're talking about this case where y squared plus x squared over 4t was equal to 9, if t goes to infinity and x squared over 4t is negligible, then y is 3 and negative 3. The black line on top and the bold red line on the bottom. Basically, the ellipse is elongated along the x-axis so much that it becomes two parallel lines. Okay, so let's move on to problem 3. This is basically another unsteady flow field. The velocity field is given. As you can see, both the u and v components have time dependencies. We are again asked to find the streamline, equation for streamlines. We are also asked to find the path line of a particle that passed through the point 1 and 1 at time t equal to 0. Then we are asked to compare the streamlines that go through the same point with the path line of the set particle. Okay, so let's start with the streamline. Again, dy over dx is small letter v over small letter u, which for our case is yt over 1 plus t x. Play with the equation, I get dy over y is t over 1 plus t dx over x. I'm just keeping all the t terms on one side of this equation. You don't need to do it. I'm just doing it for convenience. Now I can make the integral. If I do, I get natural log of y is t over 1 plus t natural log of x plus, of course, the integral constant. Playing with this equation the same way that we played with the equation in problem 1, I get that y is constant c times x to the power of t over 1 plus t. So this is the equation for the streamline. Again, by changing the value of c, you can find the streamlines at any given time. Now, next up is finding the path line. So let's focus on the path line here. Based on the equations that we derived in the lecture, in the video of basics of fluid mechanics, I will put the link to that video in the description down below. We know that for the path line, I can say dx is actually u dt, and dy is actually small letter v dt. Plugging in the values for u and v components, I get dx is 1 plus t x dt, and I also get dy is yt dt. Now I need to make these integrals. In the top equation, I can see that I have dx on the left-hand side of the equation and an x variable on the right-hand side. So again, I have to play with this equation before making the integral. That means I need to first write the equation in this form. dx over x is 1 plus t dt. For the y component as well, I get dy over y is equal to t dt. Now I'm ready to make the integral. We are making the integral dx over x from the position, the initial position of the particle in this problem at x equal to 1 to a final location x is equal to the integral of 1 plus t dt from the initial t equal to 0 to a final term t. The same goes for the y component. I can say integral of dy over y from the initial position of this particle, which was again at point 1, 1, to its current location y is equal to integral from 0 to t dt. All right, so the top equation gives me natural log of x is t plus t squared over 2. And the bottom equation gives me natural log of y is t squared over 2. So these two equations govern the path line of a particle that was located at location 1, 1 at time equal to 0. So from now on, in order to plot the path line, we have two options. I can put numerical values for time in these two equations and record the x and y coordinates and put it on a graph and then connect them together to find the path line. Or I can try and eliminate time between these two equations and end up with a equation relating x and y. So both ways are okay to draw the path line. However, I'm going to try the second method to eliminate time between these two equations. So from the bottom equation, I can get that t squared is 2 times natural log of y, which means t is the square root of 2 natural log of y. Now, I know that when making a square root, you end up with two roots, positive square root of 2 ln natural log of y and negative square root of 2 natural log of y. However, we don't have a negative time, right? So we are not dealing with the negative root and just focus on the positive one here. So I found an equation that relates t to y. I can use this to eliminate time in the x equation. So going to the top equation, I can write natural log of x is equal to t plus t squared over 2, right? Which, based on the equations that we have, t is square root of 2 natural log of y, and t squared over 2 is natural log of y. So I can say natural log of x is natural log of y plus square root of 2 natural log of y. Now this is the equation for the path line of a particle that was at point 1, 1 at time 0. All right, so here we are again with this trusty website, and I'm going to generate the path line for the particle that at time t0 was at point 1 and 1. The equation is natural log of x is equal to square root of 2 times natural log of y plus natural log of y. So this purplish line here is the path line for the set particle. Now let's draw some streamlines and compare them with this path line. So we're tasked to draw the streamlines that go through this point 1 and 1 at different times, namely 0, 1, and 2 seconds. So for 0 seconds, the equation becomes y is equal to 1. Looking at the equation for the streamlines, y is equal to c times x to the power of t over 1 plus t. If the streamline wants to go through point 1, 1, c has to be 1, right? The constant is 1. So with that in mind, for t equal to 0, the streamline reduces to y is equal to 1. That is the black line here. Now, you could have predicted this by looking at the velocity vector. When t is equal to 0, if you take a closer look at the components of the velocity vector, you will see that the y component becomes 0. So the flow initially is in the x direction only. And as a result, the streamlines are parallel to the x-axis. And that's the black line here. So our prediction was right. Now, when time goes to 1 second, what happens? The streamline equation becomes x to the power of 1 over 2. That is the red line here. And when time goes to 2 seconds, I get that y is equal to x to the power of 2 over 3, which is the bold blue line here. So the purplish line in the middle is the path line of the particle. The black, red, and blue line are the streamlines of the flow at different times. Again, this is a transient or unsteady flow field, and as such, the path line is different than the streamline. And you can see that clearly here. That single particle that initially was at point 1 and 1 will follow this purple line throughout the velocity field. However, at any given time, the streamlines that go through point 1 and 1 look different, and we have 3 examples of them here in the form of the black, red, and the blue line. Okay, problem 4. Now, in this problem, we have a cylinder. The dimensions and the mass of the cylinder is given, and we know that it's been sitting at rest inside a tube, and it has been released from the rest, and it's now falling down the tube because of gravity. We are asked to find the terminal velocity here. So let me first draw a representation of the problem. So this is the tube. This is the cylinder in question. Now this cylinder is falling due to gravitational acceleration. Some dimensions are given. The diameter of the cylinder is 5 centimeters. The diameter of the tube is not given. However, we are given the gap, the thickness of the gap between the cylinder and the tube, meaning that here, if I zoom in, I get this. This is the side of the tube. This is the side of the cylinder, and this gap between them is 2 millimeters. All right, now there are a few things in this problem that we need to first define. First term is terminal velocity. You may not be familiar with this term. Now, terminal velocity is a term that is generally used to refer to the velocity of an object which is in force equilibrium. What I mean by that is this, for example, for the case of our problem, this cylinder, because of gravity, is falling down. Now we know that the scenario, that in a situation where there is no air resistance, there is no fluid resistance, or any friction force present, this fall will always accelerate because of G, because of gravitational acceleration. So the velocity of this falling cylinder will increase over time. However, here, there is an oil layer between the tube and the cylinder. Now, oil is a viscous fluid, and as a result, because of the motion of the cylinder, oil will enforce some sort of a shear stress on the cylinder. This force will behave just like friction. It opposes the motion. So after a while, this cylinder reaches an equilibrium force-wise, in a sense that the friction force is equal to the gravitational force. The velocity at which this object reaches this equilibrium is called the terminal velocity. Now, you may have heard terminal velocity referring to objects that are free-falling, maybe people that are parachuting. Before opening their parachute, they're free-falling. They reach a certain velocity and they do not accelerate any further because the sum of forces acting on them, the air resistance and the gravitational force, are equal in that terminal velocity. So they do not accelerate anymore. All right, so we define what terminal velocity is. We also refer to the viscosity and the shear stress that the oil applies on the cylinder. In order to find the shear stress, for a Newtonian fluid, which we know oil is, generally speaking, unless stated otherwise, is a Newtonian fluid, we can follow this equation. Tau, shear stress, is equal to mu, absolute or dynamic viscosity of the fluid, times d velocity dy. So in this equation, we are dealing with mu, which is a property of the fluid, and du dy, which is a property of the flow. du over dy is referred to as velocity gradient, and they represent the rate of deformation of a fluid element in this flow. Okay, so let's start with the easier part of this equation, mu. For an SAE oil with these properties, 10W-30, you can check the property tables of fluids. You can Google them or use the appendix in any fluid textbook, and you can find that mu for this specific oil at 25 degrees Celsius is roughly 0.15 Newton seconds over meter squared. So I got the number for mu. Now I need to find a number for velocity gradient. For that, we need to go back to that gap area between the tube and the cylinder. So if we focus on this gap again, I know that this cylinder, this falling cylinder, is falling with a velocity, let's call it capital letter V, right? So inside this gap, we are told that the velocity profile is going to be linear. So what does that mean? I'm going to use a very useful assumption that is valid for all Newtonian fluids and even most of the non-Newtonian fluids. And that is no slip condition. Now, what no slip condition means is that fluid particles adjacent to a solid surface have the same velocity as the solid surface. For example, here, the tube is stationary, so all the flow particles next to the tube are stationary. The cylinder, on the other hand, is falling down with the velocity v. So every fluid particle adjacent to that falling cylinder have the velocity v. Take into account that the problem suggests a linear velocity profile. I get a velocity profile like this. So the orange vector here is v, and this is the velocity profile. Now let's try and write an equation for this orange velocity profile. Okay, so let's say we are using this coordinate system. This is the x direction, and this is the y direction. Now I know that the gap is 2 millimeters wide, but for now, let's just assume that it is h meters wide instead of 2 millimeters. I just want to derive the equation in a parameter form. So the problem specifically says that we can assume a linear velocity profile in the gap. That's how we decided that the orange profile is the velocity profile that we're looking for. So let's put an equation on that profile. I can say u as a function of y is ay plus b. This is a linear profile. A and b are constants and I need to find them. I have two conditions, boundary conditions, that can help me find the value for A and B. The first condition is the no-slip condition on the tube wall. That is, at y equal to 0, there is no velocity. Velocity is 0 because tube is not moving. The second condition is that at y equal to h, on the other side of the gap, u is equal to the velocity of the cylinder, the terminal velocity. So let's put these two into the equation and find A and B. So from the top equation, I can get B is 0. From the bottom equation, I get that A is V over H. So now I have an equation for my velocity profile. U as a function of y is V over H times y. Now that I have the velocity profile, I can also find the velocity gradient, which is required to calculate tau shear stress. So du over dy is V over H. Okay, so let's go back to our equation for shear stress. It is mu du dy. However, this is shear stress. We are really interested to find the actual force or shear force that is applied onto this cylinder. Because remember, a terminal velocity is referred to the velocity of the object when the forces are in equilibrium. And let's take a look at the cylinder again. Now let's say this is the free body diagram of our cylinder. So what are the forces acting on it? I have the gravity in the form of weight, mg, dragging this down. On the other hand, I have this friction force acting in the opposite direction of the flow. Now, this friction force is because of the viscous oil that is filling the gap. I know that there is a relation between this viscous force and the shear stress. So shear stress is F over area. Now, area that we're interested in here is the area around the cylinder, the surface area of the cylinder. So I can say F is tau area, or F is going to be tau mu du over dy times the surface area of the cylinder, which is pi d, the diameter of the cylinder, L, the height of the cylinder. So I found F. Now I can write down the equilibrium for the forces in the direction of the motion. So the forces are in equilibrium. That means sigma F is 0. That means F is equal to mg. Let's play with this equation now. F is pi d L mu du over dy. Now remember this equation here? We derived the velocity profile. This is where we are going to use it now. It is equal to pi d L mu terminal velocity of the cylinder over h, the gap between the cylinder and the tube, is equal to mg. Now I can solve for the terminal velocity. So I get that the terminal velocity v is mgh over pi dl mu. So all that remains now is plug in numbers and calculate the actual velocity. So velocity is mass of the cylinder is 2. G, the problem says we can take it as 10. H is the gap. Gap is 2 millimeters, so that is 2 times 10 to negative 3 over pi times diameter of the cylinder is 5 centimeters, so that is 0.05 times the height of the cylinder is 10 centimeters, 0.1 times mu. We read it earlier from the tables, 0.15 Newton seconds per meter squared. Now using a calculator, terminal velocity is 16.97 meters per second. All right, problem 5. We have a piston that is moving with a velocity of 6 meters per second inside a cylinder. Just like last problem, we have a lubricant that is filling the gap between the piston and the cylinder. We know its kinematic viscosity and its specific gravity. We are asked to find a power loss due to friction. So let's draw a schematic of the problem. So this is the cylinder. This is the piston inside, moving, let's say, to the right with a velocity of 6 meters per second. Now some dimensions are also given. I know that the piston is 300 millimeters long and its diameter is 150 millimeters. I also know the diameter of the cylinder. The diameter of the cylinder is 150.2 millimeters, right? Okay, so what does this mean? It means that the gap between the piston and the cylinder is 0.1 millimeter on either side. So if we focus here, the gap is 0.1 millimeters. Also here, the gap is 0.1 millimeters. Okay. Other than that, we know the specific gravity of the lubricant, and we also know the kinematic viscosity. Now, first things first, in the problems, that the dimension of the gap or the distance between the two solid objects is relatively small compared to the other dimensions. For example, here the gap is 0.1 millimeter, while the diameter of the piston is 150 millimeters, right? So the diameter of the cylinder is 1500 times greater than the dimension of the gap, right? So it is relatively small. In these scenarios, we can assume a linear velocity profile in the gap. That's the first thing I wanted to mention. Let me write it down here. Now, second thing is the definition of power loss. We know that the classic definition of work is force times the distance that the object moves. Now, of course, work loss is the work loss due to friction. I can put a loss here, and that would be F, the friction force, times the distance that the object moves. However, here we are interested in the power loss. Now power, by definition, is dW dt, where t here represents time. Now let's play with this a little. I will have d dt of F, friction force, times d. Okay, so d dt of F times d. Now, what is F here? Just like the previous problem, F here represents the friction force or the viscous force due to the lubricant, to the fluid. So I can actually say F is the shear stress applied on the piston times the surface area of the piston. Also, tau is mu du over dy, right? Now, as you can see, tau, the shear stress, is not a function of time. And so F is not a function of time. And as a result, in this term, I can take F out of the derivative. So I will end up with P power is F ddt of the distance that the piston is moving. Now, ddt of the distance that the piston is moving is a definition of the velocity of the piston. But this is actually the velocity of the piston, meaning that P, power loss due to friction, is F times V. So this is the equation that we are going to work with. Now here, velocity of the piston is already known, 6 meters per second. The only unknown is the F. In order to find F, I need to find the velocity gradient. So zooming on the gap again, I have this piston moving to the right with a velocity of 6 meters per second. And then I have the wall of the cylinder, which is stationary. And again, I can assume a linear velocity profile in the gap because the gap dimension is relatively small compared to the other dimensions of the problem. So I am again looking at a velocity profile that looks like this. And I need to find an equation for it. This is basically the same equation that we found in the previous problem, but I'm just going to drive it again here for practice. This is the x direction, and this is going to be the y direction. In this case, my linear velocity profile looks like u as a function of y is, again, ay plus b. I have to find a and b, so I'm going to use two boundary conditions, both no-slip conditions. At y equals 0, on the cylinder side, there is no velocity, u is 0. And at y equal to h, let's say that the gap is h meters wide. At y equal to h, I have the velocity is equal to the velocity of the piston, capital letter V. I know that it's 6 meters per second. I just want to keep everything in parameter form. So using these two conditions, I get that u as a function of y is V over h times y. Now from this equation, I can immediately conclude that du or dy, the velocity gradient, is the velocity of the piston over the gap. All right, so using the red and the blue equations here, I can find tau, shear stress. So tau is mu times velocity over the gap. Here, we have a problem. I don't have the value for mu. What I have is the kinematic viscosity. Now, kinematic viscosity, show it with nu, is mu over rho, the density of the fluid. However, I don't have the density, I have specific gravity. Now, specific gravity, show it with Sg, is the ratio of the density of the fluid that we are interested in to the density of water. So, combining everything that I have here, I can say tau is density of water times specific gravity times kinematic viscosity times the velocity of the piston over the gap. Okay, but we are not done yet. I still need to find the F, the force due to the viscous flow. Earlier, we said that F is tau times the area of the piston. That means rho of H2O times Sg times nu velocity over the gap. This is tau times the area of the piston, which is pi d L. D is the diameter of the piston and L is the height of the piston. The power loss due to this force of friction is F times the velocity of the piston. That means P is pi dl rho of H2O, specific gravity, kinematic viscosity, velocity squared over H. Plug in numbers, you get that the power loss is 1,311 watts. All right, problem 6, our last problem. We have two parallel discs that are separated by a layer of lubricant. The upper disc is rotating above the other disc, and the angular velocity is known, it's W. We are asked to find an algebraic expression for the torque needed for this motion. So let me just draw a schematic of what's going on here. So we have two parallel discs. This is the bottom one, sitting there stationary. And then we have this disc on top of it that is rotating with a velocity, an angular velocity of W. Now these two discs are parallel. Let's say that the diameter of the disc is capital letter R and the gap is h wide. Okay, so let's take a look at this problem. So this is the top disc. It is rotating about its center. The center is not moving. The entire disc is rotating about this center with a velocity, angular velocity of omega. Now let's take a look at a fluid element adjacent to this disc. First thing first, this is a disc rotating about its center. So based on experience, it is best to use the cylindrical coordinate system here. Now the fluid element that we want to take in a cylindrical coordinate system looks like a ring. This is the fluid element that I want to analyze. So this is actually, I'm looking at it from an isometric perspective, but this is actually a ring. The center of this ring is at a distance r, small letter r, from the center of the disk. Now, if I ask you that I have this ring that is rotating about the center of the disk, what is the velocity, linear velocity of this ring? All of you already know that the velocity will follow this equation, r times angular velocity, right? What that means is that every location on this ring has a velocity of r omega that is normal to the radius of the ring, right? All right, so we established that the fluid particles that are adjacent to the upper disk move with the velocity r omega, because that's the slip condition, no slip condition, right? Any fluid particle adjacent to the solid has the same velocity as the solid. Here, any fluid particle adjacent to this red element has the velocity r omega. But that's not all. I know that there is another disk sitting on the bottom, right? Now the bottom disk is stationary, so the fluid particles next to the bottom disk are not moving. So if I extend my fluid element, this ring fluid element, from 2D to a 3D shell, then I will have something like this, right? So I extended my 2D ring element into a 3D shell element, okay? So I will have this shell. Now, inside the shell, if the gap between these two disks, h, is relatively small compared to the other dimensions of this problem, namely the radius of the disks, I can assume that the velocity profile inside this shell is linear. Now, what I mean by that is on the top of this fluid element adjacent to the moving disk, fluid particles are moving with a velocity rw. On the bottom of this fluid element, on the bottom next to the stationary disk, the fluid elements are not moving. I can assume that the change of velocity in this gap inside my shell element is linear if h is relatively small compared to r, capital letter R. So with that assumption, basically I can find a velocity profile just like the last two problems. For a second, let's focus on what we actually need to find a torque. So by definition, torque is force times the radius of the force, right? So for this problem, for this element that we have, let's say the fluid element, this shell element, is causing a friction force, F, in the opposite direction, the motion. So the amount of torque that this dF of this shell element is causing is dt, the torque, is R dF. So far, so good. We know that torque is F times the radius of the force, or the arm of the force. For this fluid element, this red element that I have here, I know that because the fluid inside is viscous, I have some sort of a friction force. I'm going to show it with dF, and it's opposing the motion. So the amount of torque caused by that dF is dt. Now, what is dF? I know that the friction force due to a viscous fluid is tau shear stress times the area that the shear stress is applied to. So for our case here, dF becomes tau shear stress of the fluid times dA. Now what is dA? dA is the area that the shear stress is applied to. For our shell element here, dA is actually this area. This is where the disk is in contact with the fluid, right? This is the dA that we are interested in. So I can say dF is tau times, now what is dA here? dA is 2 pi r dr. So now let's isolate the equations that we actually need. This is the first equation that we need, that is relating the torque to the friction force, the viscous force. This is the second equation that relates the viscous force to the shear stress. All we need to do is find a relation for shear stress now. Okay, so I'm going to focus on my shell element here in the gap, right? I know that the top of the fluid element is moving with the velocity rw. The bottom is not moving, it's stationary. So assuming a linear profile, I have this. I can find the equation for this linear velocity profile. We've done it before in the past two problems, so I'm not going to do it in details again. I'm just going to tell you that the linear velocity here, just like the ones that we found in problems 4 and 5, is u as a function of y, if this is the y direction, is rw over h y. This means that the velocity gradient du over dy is rw over h. Now finally, the last equation that I need is tau is mu du over dy. So I have four equations and I can combine them all together to achieve a single expression. So dt, the amount of torque, is r times I'm going to combine everything together to find df. df is tau. Tau itself is mu times du dy, which is rw over h, times the area of the fluid element, 2 pi r dr. So to clean things up, I can say dt is 2 pi mu w over h r cubed dr. I can now make the integral to find the total torque required to move this disk. So total torque is going to be the integral from the center of the disk to capital letter R, 2 pi mu w over h r cubed dr. Now everything before r cubed is a constant, so they jump out of the integral. You have 2 pi mu w over h, integral from 0 to capital letter R of r cubed dr. Finally, total torque is pi mu w over 2h r to the power of 4. Like always, thank you for staying till the end of this video. If this video helped you in any way, I would appreciate it if you could leave a like or a comment and maybe subscribe for future videos. Thanks again and see you in another one.